So I will start with the introduction of this open-ended lab experiment. Rotating machines often contain masses that are not perfectly distributed about the axis of rotation. So this uneven mass distribution produces unbalanced force and moments, which can cause vibration, noise, and also excessive drag. Balancing is the process of correcting these effects to ensure smooth and stable operation of a rotating system. That's why we do this open-ended lab experiment of static and dynamic balancing. So the first part of the experiment is static balancing, which is to observe the static balancing condition of four mass system. So now we will moving on to theory of static balancing of the shaft. So the concept of it is when the shaft with attached masses is stationary or rotating at low speed, there will be a gravitational forces. If the forces are unbalanced, the shaft will experience the rotating of the shaft, bending, and also single plane unbalance. The static balance ensures that the shaft to remain at any angular position at rest and improve low speed rotating system. Next is the theory for more than two mass system. For the system with more than two masses, balancing will be achieved by calculation, which is resolving forces in horizontal and vertical planes, or using the graphical force vector polygon method. The static balance is achieved when the force polygon closes, indicating zero resultant force, and also the center of mass lies on the axis of rotation. So, for the components that we'll be using in the static balancing experiment, the components are mass block, weight buckets, small steel balls, and also the Allen key. Next, we will be moving to the procedure. First, remove the perspex dome and draft belt, then install the extension pulley. Next, mount the balancing blocks on the shaft and set initial angular positions. The third one is to determine the out of balance moment WR by adding the steel balls at 90-degree rotation occurs. Continue with the first step. The first step is calculate the fourth block for the shaft using moment polygon or analytical method of calculation. And the last step is verify that the shaft has achieved static balance by mounting the fourth block on the shaft.
Now I will present the results for the static balancing experiment. So in this experiment, the out of balance moment, which is WR, for each mass block was determined experimentally using weight buckets and small steel balls. So each block was rotated until it reached a 90-degree displacement, which represents its static imbalance under gravitational forces. So the WR values obtained for all the blocks were recorded and used in the static balancing calculations. Based on these values, the corrective mass and its position were determined to eliminate the resultant force acting on the shaft. After mounting the calculated corrective block on the shaft, the system was observed to remain stationary at different angular positions, indicating that static balance had been achieved. So next is the discussion of our results. The static balancing process involves measuring the gravitational imbalance of each block using bucket weights and steel balls. Blocks with higher WR values require a greater applied weight to reach the 90-degree position, which indicates a larger degree of static imbalance. The variation in WR values among the blocks confirms that the mass distribution was non-uniform in the initial setup. By adding an appropriate corrective mass, the resultant gravitational force acting on the shaft was reduced to zero. Once static balance was achieved, the shaft was able to remain in equilibrium at any angular position without a tendency to rotate. This demonstrates that the static balancing is effective in eliminating single plane unbalanced caused by gravity, especially for stationary or low speed rotating systems. So, for the conclusion for static unbalance in the four-mass system was successfully identified by measuring the out of balance moment WR for each block. The recorded WR were then used to determine the required corrective mass to eliminate the resultant gravitational force acting on the shaft. Static balance was confirmed when the shaft remained stable at any angular position without rotation. Overall, this experiment demonstrates the importance of static balancing in reducing gravitational imbalance and improving the stability of rotating systems operating at low speeds.
Okay, now we're going to move from static to dynamic balancing. We now consider what happens when the shaft rotates. As the masses spin, centrifugal forces are generated. If these forces are not balanced, the shaft will experience vibration, bending, and twisting moments. Dynamic balancing aims to eliminate these effects, ensuring smooth and stable rotation even at higher speeds. For systems with more than two masses, dynamic balancing requires satisfying two conditions, which is zero resultant force and zero resultant moment. This can be achieved either by resolving forces and moments in horizontal and vertical planes, or graphically using a moment polygon. When the polygon closes, we know the system is dynamically balanced. Before restarting the experiment, let's identify the key components that we'll be using. First, the shaft with mounting positions, eccentric discs or balancing blocks, steel balls for weight adjustment, an extension pulley, and a motor to drive the system. The procedure begins similarly to static balancing. First, we remove the perspex dome and the drive belt. Then we install the extension pulley. Then we mount the balancing blocks on the shaft and reset their initial angular position. To determine the out of balance moment, or we known as WR, we add steel balls until each block rotates to a 90-degree displacement. After measuring WR for each block, we calculate the angular and actual position for the remaining blocks using either graphical or analytical methods. Once all blocks are assembled at their calculated position, we run the motor and observe the shaft's vibration. Minimal vibration confirms that dynamic balancing has been achieved.
Now I will move on to the results of our experiment. In this experiment, the out of balance moment WR for each mass block was determined experimentally using eccentric disc. Each block was rotated until 90-degree displacement was achieved, which represents the magnitude of its out of balance movement. So the measured WR values for all of 4 blocks were recorded and used in the balancing calculations. Based on these values, the angular positions and axial distances of the remaining blocks were determined using the graphical moment polygon method. After assembling all the blocks at their calculated positions on the shaft and the running motor, the shaft was observed to rotate smoothly with minimal vibration. This indicates that dynamic balancing was successfully achieved. Next is the discussion of our result. So dynamic balancing was achieved when both conditions were satisfied, which are zero resultant centrifugal force and zero resultant moment. When the mass blocks were placed at their correct angular and axial positions, the shaft rotated smoothly without noticeable vibration. This shows that the calculated positions were effective in cancelling out both the force and moments acting on the shaft. However, during the experiment, we observed that even a slight displacement of one block caused noticeable vibration. This indicates that dynamic balancing is very sensitive to positioning accuracy. Minor deviations from perfect balance may have occurred due to limitation of measurement accuracy, slightly block misalignment, and mechanical friction in the system. Despite these factors, the overall results still demonstrate effective dynamic balancing of the 4 systems. In conclusion, the dynamic balancing of the shaft was successfully achieved in this experiment. The system was balanced by ensuring both zero resultant force and zero resultant moment, which are the key requirements for the dynamic balance. The smooth rotation of the shaft with minimal vibration confirmed that the calculated mass positions were correct and effective. Unlike static balancing, which only eliminates the resultant force, dynamic balancing also considers the moment effects that can cause vibration during the rotation. Therefore, dynamic balancing is more suitable for systems with multiple rotating masses and high-speed applications. Overall, this experiment helped us better understand the importance of dynamic balancing in rotating machinery.